Hello children, and welcome to the video tutorial for a little bit focused on this free response, but we're going to try and make up for lost time by going over a little bit of the electric field and electric field lines. So let's do that by looking at this first problem. You guys don't need to worry about the second problem. This is for a subject that we're going to do later in the week, so be sure and hang on to this free response. So let's look at this. We've got two charges, or two particles here, M1 and M2, and they're separated by 0.02 meters on an insulating string. So that means that the string does not conduct electricity. The objects are initially at rest on a horizontal, non-conducting, frictionless surface. The effect of gravity on each object due to each other is negligible, blah, blah, blah. So, calculate the tension in the string. Okay. Well, if we break this down, and if we look at each mass here, we got M2 and M1, and both of these are negative. If we just look at one mass in particular, let's just look at M2. And let's see what kind of forces it's dealing with. First, it's got a repulsive force from M1, which I am going to draw heading out to the right here. So this is the repulsive force from M1. But we also have this tension force coming like that. Imagine that's going straight down the string. And so, since they tell us that the objects are initially held at rest, then that means that the sum of my forces must equal 0. So, for that to be the case, we've got to think about, okay, what are the two forces that I am dealing with here? Well, if I make Fm2 be negative, or make this be positive, it doesn't really matter so much because, well, we'll see here in just a second. So what I'm going to do is I'm going to say that my tension force minus my force from M1, not M2, is going to be equal to 0. Okay, so let's set this up. We got tension, and then minus this force is given to us by Coulomb's law, which says that come on, tablet, Q1, Q2 over R squared. Okay, now the charges here are equal in magnitude, so really I can just make this Q squared. So I'm going to go K, and then I'm going to go lowercase q squared all over R squared, and that is my force from M1 to M2. Now, let's substitute in our values. They told us that the charge on each particle was -4 nanocoulombs. And again, I need that in coulombs. So you can make K. A lot of times you can assume that K is 9.0 times 10 to the 9th. And again, the units on that are Newton meter squared over Coulomb squared. So I'm going to go ahead and plug that in for K. 9.0 times 10 to the 9th times. Now, since my charge is negative, then I've got -4. And then it's nanocoulombs, so that's 4.0 times 10 to the -9th. And then that is squared, all of that divided by what was our length? 0.02 meters squared. Okay, so I can simplify that, add that to the other side, and I get a tension force of 3.6 times 10 to the -4 newtons. Now, if I had done it the other way around, and I had said that 0 equaled Fm1 minus tension, I still would have gotten the same answer because, I mean, if you think about it, this would give me a negative value, and so I add that to the other side, and so all you get is the same answer just with the signs flipped. And so the sign convention doesn't really matter, and they award you points either way depending on what sign convention you use. Here I used M2, and so I would get a tension force. Since I made the right negative, I get a tension force that is positive. Again, it doesn't really matter what you do, just as long as you keep the same sign convention throughout the problem. So let's look at part B. Part B asks us to, it says, illustrate the electric field by drawing electric field lines for the two objects on the following diagram. Okay, so I'm going to recreate that right here. So I've got it there, and then we'll go right about there. Okay, now, the key to electric field diagrams is to imagine that you have a small positive charge and you draw, in a sense, the tangent to what the net force would be on that positive test charge. So if my charge was right here, right in the middle of these two equally charged particles, I don't really have a net force. So right in the middle here, you don't have any electric field lines. So in other words, your lines kind of reach an asymptote right here in the middle. Because right there in between those two charges, their attractive forces to our positive imaginary test charge cancel out. And so what ends up happening is you have kind of a situation like this, where you've got each line approaching an asymptote, and again, always heading towards a negative charge, and then arriving at the surface perpendicular to that surface. Okay, so right here would be a right angle. Okay, and so what's nice about this is if you draw a line over here, you can mirror it over here, and you can also mirror it underneath like this. So that wasn't very good, but you get the idea. You mirror it underneath, and so imagine if we put our positive test charge right here. Well, it would feel attractive forces from both of those particles, but it would just go straight towards that particle, and vice versa over here. Now, another key thing, again, you always want it to be perpendicular to the surface. You always want, in a sense, towards a negative charge and then away from a positive charge. They must never intersect. In other words, your field lines must never intersect each other. And the number of lines is proportional to the charge. So since these two charges are the same, that means that if I have 4 lines over here, I've got to have 4 lines over here. And so what we can do is just kind of extend this out a little bit like that, and maybe draw one more kind of like this. Okay, so that would be a pretty acceptable drawing. Again, my drawing is not very good, but it's an acceptable drawing because since they're equal charges, they both have 5 lines. And again, it's arbitrary how many lines you choose. It just needs to be proportional. So let's say that this charge over here was twice that of M1. Well, then I would have twice as many field lines going to this charge as I did this charge. Okay, but since I don't, since they're equal charges, they've got equal field lines. Again, it's totally arbitrary. I could draw more and more lines because there is field right here in these empty spaces. But again, you don't need to draw so many lines that you just confuse yourself. Okay, so now that was part B. Let's look at part C. So now they're telling us the masses of the objects M1 is 0.03 kilos and M2 is 0.06 kilos, and the string is now cut. And they want to calculate the magnitude of the initial acceleration of each object. Okay. So let's go back here. Okay, so now my string is cut, and I know that M1 is 0.03 kilos and M2 is 0.06 kilos. That didn't work. Okay. And I know that they are going to have an acceleration in this direction, and they want to know the initial acceleration. Okay. Well, initial acceleration is just, again, you start with FMA, and you're going to use that for each particle. Okay, so initially, if the string is cut, then that means that my repulsive force that we found earlier, in a sense 3.6 times 10 to the minus 4, that is what my repulsive force is equal to. Because now that I have no tension, before my objects were held at rest, and so my tension equaled my repulsive force. Well, now that my tension is cut, the only force that I have initially is this repulsive force, which is equal to my tension. So it's just in the opposite direction. So I'm gonna switch sign conventions, and I'm gonna take left to be negative, and I'm gonna take right to be positive. So initially, over here, my force, my repulsive force, is in the negative direction. So I've got negative 3.6 times 10 to the minus 4 equals 0.03 A. So again, I solve for A, and I get an acceleration force here, or excuse me, an acceleration of negative 1.2 times 10 to the second. Or excuse me, times 10 to the minus 2. That would have been really fast. And that is for A1. And so A2, I go about the exact same way, except here I plug in positive because I know my repulsive force is positive, and I plug in 0.06 for M2, and I get a value of 6.0 times 10 to the minus third meters per second squared. I mean, this makes sense that this particle is accelerating faster because it is lighter, because they are both experiencing equal repulsive forces. So that would be your two answers for C. Now, D asks us, on the axis below, qualitatively sketch a graph of the acceleration of the object of mass M2, and this is confusing. It dragged this T from somewhere, I don't know where, but it's M2 versus distance between the objects after the string has been cut. Okay, so let me recreate this graph over here. And so we've got acceleration, 0, and distance. Okay, and so my acceleration initially starts out at 6.0 times 10 to the minus third meters per second squared, but that is at a distance of 0.02 meters because that's how far apart they were initially. So what I would do is I would go 0.02, and I would start just qualitatively here, and I would let the graders know that your acceleration starts at this point. You could even start and say it starts at 6.0 times 10 to the minus third. You don't have to do that, but this I would definitely write. And so then what happens is that as that distance between those particles increases, the force that is acting on them, that repulsive force, starts decreasing. Because the force is equal to Coulomb's law, which we set up here. And so we see that force is inversely related to radius squared. And so what you've got is a graph that looks something like this. And again, it would approach an asymptote around 0, because they would never have 0 acceleration as long as r approaches infinity. And so that would be your graph right there. And again, with this type of problem, this graph is worth 3 points. So if you know how to qualitatively describe this with a graph, you get 3 points. And then the next question asks you, describe qualitatively what happens to the speed of the objects as time increases, assuming that the objects remain on a horizontal non-conducting surface. So with that last question, again, it's also worth 3 points. So you got 6 points total for describing the speed, or the acceleration and the speed of the objects after the string is cut. And so for E, for this last question, you know that the speed is going to continue increasing, but it's going to continue increasing at a slower rate as your distance increases. And it's going to approach a constant value, in other words, like a terminal velocity, as your distance increases. So, a lot of points available for just knowing how to qualitatively describe something. So that's that. Again, we'll review more electric field lines, and yep, good luck.